sit back and relax, knowing that your interview with Florian is a thing of the past now. But I hate to break it to you, there are still 2 things that you have to do before we can accept you to Harvard. So the first is you have to go on a housing tour. Devastatingly against Matt and Matt, which actually comes very highly regarded. Definitely check that out. And the second thing you have to do is you have to hug Felix Barber. Felix Barber. So why would you ever want to hug this stallion of a man? Maybe it's the wind in his hair. Maybe it's the beer in his belly. Perhaps it's the thunder in his thighs. Actually, it's the fact that his hugs have an incredibly therapeutic power. And we all know that we would not be able to make it through grad school without them. So to help you guys out, because I know that this is one last challenge you have to do, I prepared a couple of pro tips as brought to you by the G1 class about how to approach and hug Felix. So Sean writes that it's best to approach Felix while he's eating. That way he'll be in a better mood and he might actually be willing to take his hug to the next level. Allison writes, don't sweat the details. Felix is willing and receptive to take hugs from the front, back, and side. Don't you worry about expressing your personality when it comes to hugging Felix. Finn tells us, be careful, don't be too eager. If Felix isn't ready for you, he will not reciprocate that loving feeling. And finally, Matt Smith tells us that if you've had just an awful day and you're feeling down on yourself, commit to that hug 100% and Felix will take you into the healing bosom of his Maori self. And Felix, I'd just like to say from me to you, we all love and support you, and we'll be waiting for you with open arms at the end of this talk. And audience, buckle up, because Felix Peter Joseph Kane Barber is about to talk to you.
Wow, okay, that was quite something. Thanks, Janelle, for a great talk. I want to start this with a video, so I hope you'll bear with me for just a second while I get that set up. So today we are going to be talking about the common European starling, the Sturnus vulgaris. What you can see here is a flocking event, which is one of the series of measurements made in the winter months between 2005 and 2007 by a group based in Rome, Italy. The thing which I want to draw your attention to here is not just the fact that the collective action here is in itself pretty astounding and quite beautiful. It's the fact that the correlations, the ability for this flock to rapidly adjust its flight path are very rapid, and the fact that the flock itself is able to swiftly adapt to some environmental cue, be it a tree or some kind of response that's needed. This is going to be the subject of our talk, this kind of flocking behavior. So I just wanted to start out by showing you something. It's actually a video from the supplementary information at the end of the paper, so I think they just decided to include it as sort of a bonus, like you got to the end. It was nice of them. Okay. So that's done. There we go. Don't even need to do anything. Okay, so this is what we are studying today, ladies and gentlemen. The European... Oh, I'm sorry, I misspelled this actually. That should be... The point of this talk today is to talk about the fluctuations, about the average velocity which occur within these flocks. So to start off with, I would like to visualize what one of these flocking events might look like. We represent each bird by its individual velocity, which is what these measurements by this group that I mentioned earlier are able to do. Then this is what a typical flocking event might look like. If I then subtract the average velocity from each individual bird within this flock, then I get something which looks a little bit more like this. The interesting structure here that I really want to draw your attention to is this domain structure where I have local order in the sense of deviations about the average velocity correlated over length scales which can be very, very large relative to the size of the flock itself. The size of these domains is characterized by this Greek letter psi, which I'm going to call the correlation length, and that's going to be a notation which I'm going to remain consistent with throughout the talk. So why are we interested in this? The interesting thing about these domains is the fact that they are scale-free. Now what do I mean by that? Well, what I mean is that if I consider the correlation length for a range of different flocks of different sizes, then the correlation length will scale linearly with the size of the flock. If you stop for a second and think about that, then that's actually quite a profound observation, because if I think about information propagation within these flocks, I have some external perturbation, and then that causes the birds on the side to deviate from their flight path. Then that information needs to propagate throughout the flock. But within the flock, there are only local neighbor-to-neighbor interactions between neighboring birds. So for information to travel as effectively within a flock of size L as it will within a flock 10 times that size, which is effectively what the scale-free behavior is meaning, that's quite impressive. So this is encapsulated in one of the relations which we're going to introduce here. So what this mathematically means is the correlation length for a flock whose size L is scaled by some factor B is exactly equal to B, that same factor, times the correlation length of a flock of size L. Is that clear? If there are any questions at any point, feel free to stop me. So this is pretty incredible, and so we want to try and and that brings us to the subject of the paper that we're going to talk about today. The paper is impressively titled "Social Interactions Dominate Speed Control in Poison Natural Flocks Near Criticality." It's a collaborative work between researchers based at Princeton here in the US, researchers in France, and some researchers based in Italy who produced the paper. It was published in the Proceedings in the National Academy of Sciences in May 2014. So when we get onto the subject of scale-free correlations, then it turns out that physics actually has quite a lot that it can say about this. And so one of the things that I want to start up with, now that we're into the body of the talk, is talking about the concept of criticality, which I am sure you have all met in the context of a classical gas. This is the phase diagram for a generic gas, making transitions between being in the gaseous state, the liquid state, and the solid state. Here we have some experimental parameters, the pressure and temperature of this gas, which we are free to adjust and we can tune transitions between these states if we want to. Something which is well known is that if we approach certain points within some phase diagrams of certain systems, known as critical points, then very interesting things start to happen. Those systems start to become correlated. Fluctuations about the average density, in this case, become correlated on length scales, which can be arbitrarily large as the system itself. What this means, the correlation length, psi, as I approach criticality, this is the critical point, becomes arbitrarily large. Now this is exactly the kind of behavior that we want to try and explain in these flocking birds, because we saw that the correlation of these fluctuations scales with the linear size of the system. And so this is one of a series of analogies that people have been thinking about in the context of biology in relation to whether biological systems are in some sense poised at some critical point. But what we want to answer within this paper, or try to answer, is whether or not this is just real life, or whether it's fantasy. So we want to go to our good friend's Queen. I'm not going to sing it, but you'll hear it later. So is this the real life? Is this just fantasy? According to the landslide, I really want criticality. Open your eyes, look up to the skies, and see. And that's exactly what these researchers did. So what these researchers try and do is produce a model which is going to have some predictive power to predict these long-scale correlations. Now, the way that they do this is using the field data which has been measured by these clever Italian scientists. They try to make a minimally structured model which is going to be consistent with certain experimental observations made from that data. What does minimally structured mean? That means that the distribution of velocities within the flock will be, in some sense, the most random, so that it will be consistent with those observations, but will, aside from that, have as little structure as possible. That can be made precise in a way which I won't get to in this talk. But what this leads to is the generic structure of a probability distribution, I hope you'll bear with me here, which looks something like this. So on the left-hand side, we have the probability distribution for a set of velocities of the birds within our flock. I've indexed the birds by some index I, which ranges from 1 to n, where n is the number of the birds in the flock. This is equal to 1 upon z. This is just some normalizing factor, because we know that the sum of all the probabilities should be equal to 1, times some exponential of some lambdas and some o's. What are these lambdas and o's? The o's are observables, so these are the things that we can measure in relation to our system. So it might be, for an example, the mean speed. Actually, that's one of the things that they do use. The lambdas are there. These are parameters which we have to tune so that this generic probability distribution meets the experimentally observed values for the expectation values of these observables. So that the expectation value of these observable parameters, for example, the mean speed, predicted by this probability distribution should be equal to the experimental value. Hope that's clear. So which observables should we use? Well, the researchers here choose to use 3 particular ones. And again, I hope you will bear with me. I will go through all this in great detail. So just broadly at first, we have Q, which measures in some sense the local deviations between velocities of neighboring birds. We have the average speed, and we have the average squared speed. So what is going on with this Q? It looks kind of complicated. Well, what it is, again, we have a normalizing factor here up front, this V0. That's just to make Q unitless. You don't really need to worry about it. N here is the number of birds in the flock. Here, NC is the number of nearest neighbors. What that means is it's the number of neighbors that a bird takes into account when it's making decisions about how it's going to orient itself and how it's going to, how fast it's going to fly. Here, we are summating of the neighboring birds, and these represent the velocities of the I and J birds. So what this Q is doing is it calculates the squared difference in velocity between neighboring birds, averages that over the neighbors for a specific bird, and then averages that over the entire flock. Any questions? Yeah?
How did you choose what's the neighboring bird?
Yeah, that's a very good question, because there seems like there's some level of something slightly arbitrary about that choice, right? So that's something that actually fit with this model. And the numbers that they come up with vary from flock to flock. I think in general it comes out to be around 15. That's actually slightly higher than some other estimates.
15 what?
15 neighboring birds is how many they.
15 closest birds.
Yeah. But you got to remember that the size of these flocks can scale from the low hundreds to up to 1 million birds. So there's a huge. These can be huge, gigantic. So this kind of order is really impressive. Yeah. So now we need to make a minimally structured model which is going to be consistent with these three observables. And again, we're left with this thing. We have to figure out how we're going to do this. It turns out that these researchers are quite clever. And so what they do is it turns out that for this probability distribution, it's mathematically equivalent to enforce that this distribution reproduce the experimental observations of those observables. It is entirely equivalent to maximize the probability of the observed experimental data. And so in that case, what we need to do is we need to maximize the probability of the observed experimental data. Now, we have 3 observables, and remember those lambdas that I was talking about before? Well, those are free parameters which I need to tune in order to maximize the probability of the experimental data. So that's what I'm doing here. I have these 3 parameters, J and G, which you haven't seen before, and NC, which you have seen before, which is the number of neighboring birds. So it turns out that part of this can be done analytically, which is something that I've suppressed, but that allows me to express J and G in terms of NC. So I have just one remaining free parameter in my model. And I then calculate the log likelihood of the observed data and calculate that for a range of different values of NC. So then I pick the one which gives me the highest probability, and that fixes those 3 parameters, J, G, and NC. So from this point on, I've got a fixed probability distribution. Are there any questions about that? No? Okay. Cool. So from this point on, I have a model which is entirely fixed, and there is no further fitting taking place. Anything from this point on is predictive. And so now the good stuff comes. To do that, I need to make precise some ideas about fluctuations and correlations that I was talking about before. So the correlation function, C of R, is what I'm going to call it. It's a function of distance between the 2 points which I'm analyzing. To give us some intuition about that, if I consider say I consider 2 birds at distance R, at separation R. If they have speeds which are correlated, in the sense that they both deviate in the same manner relative to the average speeds, so they're both greater or they're both less than, then that leads to a correlation function which is greater than 0. If they're totally uncorrelated, then you would expect that there should be no correlation between them, so my correlation function should be equal to 0. And if they're anti-correlated, i.e. if one is faster and one is slower, then I should have my correlation function less than 0. So what this looks like is it starts out positive, because if I calculate the correlation of something with itself, like at R equals 0, then that's trivially correlated, right? So it starts out positive, and then it decreases in something like this, these systems. And the point where it crosses 0 here is what they define to be psi, which is the correlation length, which is what we're interested in these systems. So that's why I'm introducing it here. Now, what I want to talk about is what the correlation function looks like for the that's right.
So naively, you'd expect it won't ever go negative.
Actually, yeah, that's a good question, but there's a very good reason why it will. And the reason why it will is that I'm calculating fluctuations relative to the average.
Oh, right.
So
Okay,
I'm always going to have some which are greater and some which are less. Yeah, cool. Good question, thank you. So here is what the data looks like for a single flocking event. I have a correlation function which decreases in roughly the same manner that we saw just before. Now, if I then calculate the values of J, G, and NC for this specific flocking event, then I can make some more predictions. The predictions are exceptionally good. Yes, they are. They agree over a very broad range of displacement values between birds. And so this is kind of encouraging, right? So now we want to see whether or not we can reproduce this scale-free behavior. So that's what we're going to get into now. We calculate the correlation lengths for a number of different flocking events with different flocks, and what they look like is here. So each cross here represents a different flocking event where I've calculated the correlation length for that flock. And here L is the size of the flock, like a linear dimension scaling the size of the flock. It could be, like if the flock was circular, then it could be like the diameter, for example. And here on the y-axis we have the correlation length. I'm sorry for the fact that this linear fit looks like a really crude linear fit. That's just my bad drawing. But if I then look at what the model predictions are, if this model is able to have some predictive power about reproducing this scaling of the correlation length with the size of the flock, then we should expect that it would agree very well. So let's see what it does. And if I place this correctly, yes I have, then it agrees exceptionally well over a wide range of sizes of flock. So somehow this model has been able to reproduce the scale-free behavior which was motivating this talk in itself. That's super interesting. And in this start, I introduced this in the context of criticality. They haven't talked about criticality since then. So we want to see whether this model is critical. And so it turns out that when I do some theoretical predictions, which I have suppressed the algebra for you, then as a specific function of the parameters in the model, G, J, and NC that we've been using, the theoretical correlation length for these systems should look something like that. Our model naturally sits somewhere here. Our model is naturally in the critical regime, and that's without us fitting it. So if we stop to digest that, that's super impressive. But it's sort of difficult to know exactly what it means, because this model isn't fundamental in the sense of we're trying to model exactly how we expect a bird will interact, but we are taking certain experimental observations, and then we're trying to reproduce a model we're trying to build a model which is going to reproduce those, and then it reproduces a whole bunch of other stuff. So yeah, I'm not sure if I'm not sure if these findings are necessarily like conclusively saying that the models that bird flocks are sitting in the critical regime, but it's certainly lending qualitative support to ideas which previously were merely qualitative and drawing hand-wavy analogies. So I think that's basically the story that I wanted to tell today. So just for some quick closing remarks. The ideas of criticality have been have found application in some other areas of biology. For example, in population genetics. If I was to consider two different strains of bacteria with mutualistic interaction between them, then if I was able to tune the strength of that mutualistic interaction, then I can determine whether or not the bacteria are going to thrive and be able to live together, or whether one is going to overall dominate and win out. And the transitions between those different states using this same kind of idea. Something else which would be really useful to be able to measure about these flocks is signal propagation, because this paper that I presented today does some work on dynamics, but each individual model is in some sense an equilibrium statistical mechanical model, because it assumes that the timescales associated with birds aligning or seeing that another bird right next to them has adjusted its velocity. The timescale between it recognizing that and adjusting its own velocity is small compared to the timescale on which the measurement is made. Yeah, so I think that's the end of my talk. And I would like to thank you very much for listening, and I'm happy to take any questions that you have now. So Sri put his hand up first.
So I guess this is like mind-blowing to me for a different reason than what you said, which is that it's not clear how they chose their data, but if they chose their data fairly arbitrarily, what this says is this model somehow is true irrespective of what external forces you apply to the flock. So even if my surroundings influence the flock in some way, they still react in a way that is still consistent to this model. Right? So basically they have to like react in the same regime of criticality irrespective of how the perturbation happens.
Yeah, I guess the idea is that neighboring interactions between birds, like the strength of neighboring interactions, is what's somehow tuned to sit in some critical regime. I say critical regime because it's the analogy with like a non-fundamental model, which is what's presented here, is kind of not as clear as all that. But sorry, did that answer your question?
Kind of. We can talk about it later. It's fine.
Yeah. Okay, and then Georgia put her hand up next. I'm sorry.
I was curious what this model is capable of telling us the level of individual bird behavior. I'm not sure if the authors talked about that, but obviously this is a really cool model, but these aren't, atoms subject to forces. These are birds executing behavior. So what does this model require that our birds be able to do? Because unless they're in 111, they're probably not doing this math.
Yeah, I
And
mean,
also, what's the tolerance to, errors? A bird was a bird stroke, and, how does a mistake in bird behavior propagate? Is this model capable of answering questions like that? Yeah.
yeah. So I mean, you can definitely see that there were errors in the agreement of the model with the experimental values at large values of R. Like down here, it gets deliberately worse. Deliberately in the sense that I drew it, and down here as well. But I'm sorry. What was the question?
My question being, what does this model tell us, biologically, I guess, about how an individual bird in this flock must behave to
Yeah.
execute?
So I guess the fact that it sits in the critical regime, if you were to interpret that from a biological standpoint, then you could say that the critical regime is one where the bird has is tuned so that it will respond. It's very responsive to nearest neighbor interactions, so it's strongly correlated in that sense. But it still has some control over its. It still exerts some control over its own speed. Yeah, so it's a combination of the two. And Mary, you can.
So it sounds like you're envisioning that the bird is seeing the bird in front of it and making a response, but you can imagine that this is all just due to wind dynamics instead, right? Right, of those large million birds flying in the same direction. So I would wonder whether there's a difference in correlation between a bird with its neighbors in front and the neighbors behind, right? Whether it's actually seeing.
Right.
Responding to something it sees, or whether it's responding to the air dynamics of the bird.
Yeah, so I guess if you were to have a gust of wind flow through a flock, then you would expect that there would, that would initiate some kind of correlation. I guess it would be difficult to separate that.
I just mean because they're moving all forward in the same direction, just like cyclists, travel behind something in the tailwind or east travel or the deformation, that actually the air flowing around the bird in front of you might cause it to move in the same direction.
Yeah, so that's one of the fallbacks of this model, in the sense that it's not like a hydrodynamic kind of model of the bird actually moving through air. So you have limitations in terms of your ability to describe its response to that kind of environmental cue.
I think you could tell that apart by seeing whether there's a correlation with the bird in front of you and behind you.
Yeah, no, that's a very interesting point. That'd be interesting to measure. In this model, they something that I didn't mention due to time constraints is that the model involves fixing the speeds and velocities of birds on the outside, and so then that is assumed to be fixed to some environmental perturbation, and then that information propagates through. Yeah.
This is really fascinating because you know a lot of fish from fish school as well.
Yeah.
And I think Ian he probably defined his model as fish. My question is, the model assumes that every bird is a follower, so where is the initiator, right?
Yeah. So that's actually another good point, which I think that in a paper that I read by the initial guys who had done the measurements were drawing on the difference between a group where there's a leader and a bunch of followers, or it's some collective decision on behalf of the group, or some state in between these. And so I am not sure what kind of where starlings exactly fall on this on that spectrum. But I guess this model inherently assumes that the birds are that it's lying on the end where birds are making collective decisions rather than there's individuals. But as I mentioned with Mary, I think the velocities on the outside of the flock are fixed. So I guess they're the ones who are able to respond to environmental cues. And so given that response, then the model is to do with the information propagation through the flock. that make sense?
Yeah.
Cool. Concept?
So, is there, or have you found in your background readings a threshold to where birds, stop acting or like trying to evade like external predators or something individually and start, using this collective behavior?
You mean like to do with the presence of predators in the environment, like this kind of flocking behavior all of a sudden occurs? Yeah. No, I'm not sure. But this kind of flocking behavior I don't think it just occurs to do with predators. They make these measurements at sunset. And I think it's not a migratory thing because this is in southern Europe, so they roost there during the winter. And these measurements are taken over the winter months. So I think it's just like a daily habit that these flocks form. And yeah, in some of the videos that I've watched, they're definitely being chased by falcons, and like the groups separate and then recombine. But yeah, that's another interesting question. I haven't seen that covered.
So in the model, coherence length versus clock diameter, it seems like the model is fitting data points with a precision that I would expect to be the noise. But
I see what you mean.
it looks like if that's reflecting something real, it's saying that the coherence length is not monotonic.
I know exactly what you mean. And that's a confusion which that's something which I should definitely explain. Each individual point corresponds to a separate flocking event, and the model is calculated, like those parameters are calculated separately for each individual flocking event. So that's why you've got this kind of like the model jumping up and down and all over the place like that. Yeah.
If you fit it for the data globally, would it still look linear?
I mean, I'm not sure if you could for the like in its current setup. I'm not sure if you could for the data globally, because you've got because I mean, if I calculate the correlation link for an individual flock, then that's already at a specific like that's tuned to the size of that flock. So yeah. Yep.
Just to clarify, it's important that the correlation length scales with flock size, because if you had a huge flock and your correlation length didn't increase, then
then
just kind of
I mean, if I think about
respond.
you're bang on. Yeah, if I think about the center of a flock, which is because in some measurements of these starling flocks, they've gone up to like 1 million members, as I mentioned before. If I think about the center of a flock like that, and I've only got interactions which are on the scale of like 15 birds, which are being talked to, and I have fluctuations which are rapidly decaying in contrast to what is seen here, then yeah, information just wouldn't propagate, and it would be not really very advantageous at all for a group of birds to flock like that.
So it's kind of like the more birds that you tell are around them, the more birds they pay attention to. Is that like
I mean,
think about it? Or?
I think the moral of the story is that nearest neighbor interactions are able to produce collective behavior and information transportation within the flock, which can extend over scales which are far, far larger than that of the individual interactions themselves. Yeah. John?
If you look at the velocity, so I assume you have like a 3D block, and if you look at velocity components, so look at like correlations in different directions, these have like darlings that they have like eyes on the side of their foot.
Yeah, they do.
So
yeah.
presumably like these far more include your neighbors in one direction than another. Like you might not see someone above you, or depending on what you could see.
Yeah, I guess it's sort of similar to what Mary was taking in terms of like the practicality. I think they just had to do this based on the distance between every birds, because I don't think they took into account the specific direction that the bird was facing. So I mean, I guess as refinement, I think I probably can't take any more questions because